everybody, welcome to take 2 of section 2.4, the second derivative. My first take, my computer did one of those blue screen freakout moments, and when I tried to come back after it restarted itself, it told me the video, that was currently only 23 minutes long, was 9,942 hours long. So obviously I could not trim that down to size. So here we are yet again. Okay, so we're going to start with a warm-up. First, we're going to look at this graph here, and we are going to fill in the chart below with either the symbols greater than, less than, or equal to. Alright, so first let's look at point A. So at A, we actually have f of A here. Alright, and so our f of a, or f of x, we need to determine, is it greater than, less than, or equal to 0? So if a point is greater than 0, that means it's going to be above the x-axis, right? So here, our point is below the x-axis, so that tells us we are less than 0. Alright, now our derivative is going to tell us if our function is increasing or decreasing. So here, our function is increasing, which means we should have a positive derivative value. Alright? So at B, our point is on the x-axis, which means our point is equal to 0. And what can we say about our derivative here? Is our function increasing, decreasing, or neither? In this case, neither would be the proper option, and if we tried to draw a tangent line at point B, we know that our derivative is the slope of the tangent line, and this slope is also equal to 0. Alright, at point C, our point is below the x-axis, so this is less than 0, and our function is decreasing, so our derivative is also less than 0. I'll go ahead and speed up for these last few points. At D, our function is less than 0, and our derivative is equal to 0. At E, our point is on the x-axis, so it's equal to 0, and our function is increasing. At F, we are above the x-axis, and we have a horizontal tangent line. And at G, we're still above the x-axis, but now the function is decreasing. Alright, so now we get to introduce the second derivative, and then we're going to come back again and look at this graph. So since the derivative is itself a function, we should be able to take the derivative of the derivative. So when, oops, my pen's a little bit big. When we take the derivative of the derivative, we call this the second derivative. Alright, the second derivative. So we write this as f double prime. So this is f double prime. Or if we write it in our Leibniz notation, we have d squared y over dx squared. And notice in our numerator, the squared goes with the d, and in our denominator, our squared goes with the x. Alright, so this is the same thing as writing the derivative with respect to x of the derivative of y with respect to x. Alright, so now we know that the first derivative, so we know that the first derivative tells us if the function is increasing or decreasing. In the same manner, the second derivative tells us if the first derivative is increasing or decreasing. Alright, so now we need to talk about what does it mean for a derivative to be increasing or decreasing. Alright, so this is the rate of change of the rate of change, right? So this has to do with concavity. Now we're going to look at some examples. So we have, let's say we have something that is concave up. Alright, so if our graph is concave up, this means our second derivative is going to be positive. Alright, so concave up, second derivative is positive. And so this means that our first derivative is increasing. Let's see why this makes sense. If we look at a point on this side over here, and we draw a tangent line like this, our function would be decreasing on this side, right? So that means our derivative must be negative, our first derivative. But if we look over here, our function is increasing, which means our derivative must be positive. So our derivative went from being negative to being positive, meaning our derivative is increasing. So if the derivative is increasing, the second derivative must be positive, means that we have upwards concavity. Alright, in a similar way, we can talk about concave down. So this is when the second derivative is negative or less than 0. Alright, so this must mean that our first derivative is decreasing. So if we see on the left-hand side, our function or our derivative is positive, while our right-hand side, our derivative would be negative. So we went from positive to negative, which means we are decreasing. So now we get to our first example, which is reconsidering the graph from the warm-up problem. And we're supposed to label on the graph where the second derivative is positive or negative. So we know that this has to do with concavity. So I'm going to go ahead and draw some dotted lines where we have changes in concavity. Alright, so we start at A. And it looks like about C is where we switch concavity. And then again we switch at about E. And then we're ending at point G. Okay, so now we need to label what is happening with the function in between all of these points where we're switching concavity. Alright, so between A and C, our function is concave down. Okay, so what does concave down tell us about our second derivative? It tells us that our second derivative must be negative. Similarly, between E and G, we are also concave down, so we should have a negative second derivative here as well. Between C and E, however, our function is concave, pen's going crazy, concave up, concave up, which means our second derivative must be positive. Okay? So now we're going to take this and use it to try to draw some graphs. So for each of the following, we are to sketch the graph of a continuous function that satisfies each of these conditions. Alright, so here we're given 3 different criteria that we need to draw a graph that meets all of them. Alright, so let's go ahead and look at each point individually, or each criteria individually, and see what it does each tell us about what our graph should be doing. So f of 2 being greater than 0, what does this tell us? Well, this says this is our y value when x is equal to 2. And the fact that it's positive tells us that we should be above the x-axis. So our point should be above the x-axis at x is equal to 2. Alright? So then our next bit of criteria is f prime of 2 is greater than 0. So f prime of 2. So this is telling us if our function is increasing or decreasing at x is equal to 2. Well, here our derivative is greater than 0, so it's positive. So we are increasing. Increasing, again, at x is equal to 2. And our last bit of information, we have f double prime of 2 is less than 0. So our second derivative tells us how our first derivative is increasing or decreasing. And it tells us if our function is concave up or concave down. So since it's less than 0, we have concave down at x is equal to 2. Alright, so the first bit of information is we should just be above the x-axis at x is equal to 2. So I'm going to go ahead and pick some point that's not at 2. Here we go. At x is equal to 2, I'm going to pick this point. It's above the x-axis. Alright, this is a rough sketch. If we had a few sample points, we would actually be able to draw this more accurately, but we don't. And so I'm just picking any point that satisfies these criteria. So if you do this without looking at my drawing and you come up with something slightly different, as long as it meets all 3 criteria, then you're totally fine. Your graph is still acceptable. Alright, so it just needs to be above the x-axis. I could have picked this point if I wanted to. Both of those points satisfy being above the x-axis, but I'm going to stay where I am. Alright, then we know that we need to be increasing. So I'm going to pick a different color and just say that we must be increasing at x is equal to 2. And then we also know that we need to be concave down at x is equal to 2. We are given no other information about what our function is doing anywhere other than at x is equal to 2. Alright? So it can do some really wild things and be totally fine as long as it is increasing and concave down at x is equal to 2. So here we could draw an increasing and concave down function. Alright? And again, like I said, it can be doing some wild things over here. We don't know. We don't really care. This is a completely fine, acceptable answer. Alright, let's go ahead and look at our second example. So here we're given that f prime of 0 is less than 0. So at 0, our derivative is negative. So we must be decreasing at 0. Alright. Then we have again the derivative, but this time at 3, and it's positive. So we must be increasing at x is equal to 3. And then our last bit of information, we have just the function value f of 1 must be positive. So again, this must be above x-axis at x is equal to 1. Alright, so I'm going to go ahead and again pick a point that is above the x-axis at x is equal to 1. Pick whatever point you want, as long as it is above the x-axis and on the line x is equal to 1. So then we must be decreasing on the left-hand side, so at x is equal to 0, we must be decreasing. And at x is equal to 3, we must be increasing. We're not told anything about concavity, just that we must be going down at 0 and up at 3, and we're going to go through the point that I've picked here above the x-axis at x is equal to 1. So the simplest line I could think of that would work for here, the simplest curve, would be a parabola. Alright, so we are decreasing at x is equal to 0, increasing at x is equal to 3, and we are above the x-axis. Alright, and our last example for this problem, we are given the second derivative of negative 2, and that is less than 0, so that's negative. Our second derivative tells us concavity. So if it's negative, that means we are concave down at x is equal to negative 2. Alright, then we have the first derivative at 0 is equal to 0. So if our derivative tells us our rate of change, and our rate of change is 0, then we are neither increasing nor decreasing, right? We are just constant. Constant at x is equal to 0. It could be just for a moment, it could be for a long amount of time, and x is equal to 0 just happens to be on that time frame. Alright, we can also say that we have a horizontal tangent line here at x is equal to 0. Alright, because our derivative is our slope of the tangent line. So if our slope is 0, we have a horizontal line. Alright, and then we are also given the second derivative of positive 2, which is greater than 0, so we are concave up at x is equal to positive 2. Alright, so let's go ahead and fill in these blanks. So concave down at x is equal to negative 2. So we got to be down around here. Concave up at x is equal to positive 2. We got to be concave up over here. And we need to be constant at x is equal to 0. Constant. Alright, have a horizontal tangent line at some point. So if we want to draw a function that fills all, or that meets all three criteria, something like a cubic function, where it flattens out in the middle and then comes down over here, something like this would meet all three criteria. Alright, so for example 3, we're given the graph of the derivative f prime of x, and we are to sketch the second derivative, f double prime of x. Alright, so this is the exact same if we just think about being given a function and we're asked to graph its derivative. We've done this before. Alright, so don't let the second derivative get in the way of knowing that you have done this before. So the first thing that we need to find is we need to find the zeros. So that's all of the places where our new graph for the second prime, or the second derivative, is going to touch the x-axis. So this is, so f double prime of x, our second derivative, equals 0. All right, so this means our first derivative is not changing. It's constant at these few points. And this happens where f prime has horizontal tangent lines. Right? So let's see, I can find 1, 2, that was a really bad drawing, but you get the picture, right? 2, 3 places where the derivative has horizontal tangent lines. So that means we're going to have 3 places where our second derivative needs to touch the x-axis. And notice there's no values on these axes here. It's a really rough sketch. All right, but so it looks like we need to touch our x-axis here, here, and here. Okay, so now we need to determine if our new function, so our second derivative, is increasing, or I'm going to say is positive or negative. So that will tell us if we are above or below the x-axis. All right, so again, we're going to look at our original graph, and our relationship between our first derivative and our second derivative is that if our first derivative is decreasing, all right, our second derivative must be negative. Okay? So here our function is decreasing here and here. All right, so we know that we must be decreasing up before our first time we're touching the x-axis, and then in between these 2 times touching the x-axis here. Okay? And now we need to determine if we are increasing and where that is happening. So, again, our original function, which is our first derivative, is increasing between the first 2 times we are touching the x-axis. So we must be positive. So I'm going to say negative and negative. And then again, we are positive. We are increasing after we touch the x-axis for the last time. And so we are positive here as well. So again, positive second derivative, okay, is the same thing as increasing first derivative, okay, and positive is position relative to x-axis. Remember, if we're positive, we're above the x-axis, and if we're negative, we're below the x-axis. And so if we have a negative second derivative, this is a decreasing first derivative. Okay, so if we are negative, looking over here at our graph, if we are negative before we first touch the x-axis, we need to start below the x-axis. And we need to come up here, touch the x-axis, and then we are supposed to be positive. So it looks like we're going through the x-axis, and we need to touch over here again, and then we need to be negative again. So we need to be below the x-axis, and then we need to be positive again. So it could look something like this, and this is our second derivative graph. All right. Now we have example 4. So the following table gives the amount of snowfall in a town called Maryville over the course of a few weeks. Part A asks us to calculate the average rate of change in snowfall between the 1st and 6th weeks. Alright, so we know that our average rate of change, well, that is our delta, in this case S, the change of snowfall over the change in time, right? So our change in snowfall would be from the 6th week we had 20 centimeters of snow, and in the 1st week they only had 2 centimeters of snow, and from the 6th week to the 1st week, so we're looking at 18 over 5, which is about 3.6, and if we wanted our units, that would be centimeters per week. So this is our average rate of change, saying that the amount of snowfall is increasing about 3.5 centimeters per week. Alright, and then part B asks, what can you say about the sign of the second derivative between the 7th and 10th weeks? Alright, so the second derivative is the rate of change of the first derivative. So we're going to need to go ahead and calculate or estimate all of the first derivatives between the 7th and 10th weeks, and then see what is happening to our first derivatives. Alright, so we need S prime, okay, from 7 to 8 weeks. We know that's roughly, right, it's approximately our change in S over change in T. So that's going to be 8 minus 12 over 8 minus 7. So that gives us negative 4 over 1, which is just negative 4. So then we need S prime from 8 to 9 weeks. And we know that's approximately 5 minus 8 over 9 minus 8. So then we get negative 3. And finally, S prime from the 9th to 10th weeks is approximately 4 minus 5 over 10 minus 9, and that's equal to negative 1. Alright, so these are all the values of the first derivative. So we are asked, what can we say about the sign of the second derivative? So again, the second derivative is telling us whether our first derivative is increasing or decreasing. Here we notice all of our values are negative, okay? However, they're getting more and more positive, right? We're going from negative 4 to negative 3, negative 1, maybe the next one would be 0, and then positive 1 if we kept going. So we are actually increasing. So derivative values, S prime values are increasing. I'm going to say are negative, but increasing, meaning our second derivative, S double prime, must be positive. Alright, and if we wanted to translate this to concavity, that means the function is concave up. If we have a positive second derivative, our function is concave up. Alright, and I will leave you with that. Don't forget to take the comprehension quiz, and we just have one more chapter or one more section for chapter 2.